welcome to lecture 10.3. Today we're going to be talking about electromagnetic waves. Now, what are electromagnetic waves and why are they important? Well, without electromagnetic waves, we wouldn't be able to see inside our bodies with x-rays. You wouldn't be able to have a glow-in-the-dark rave with black lights. You wouldn't be able to nuke your food in the microwave when you wanted to reheat it. And you wouldn't even be able to hear songs on the radio. Today's objectives: today we'll differentiate between electromagnetic and mechanical waves. We'll solve for the wavelength or frequency of an electromagnetic wave using light speed. We'll calculate the energy of a photon in a vacuum using Planck's equation. And we'll also describe the characteristics of waves on the electromagnetic spectrum. Let's start with our first objective. There are two main classes of waves: electromagnetic and mechanical. Now I want to separate these from transverse and longitudinal, which we already talked about. Transverse and longitudinal just describe whether or not the wave moves up or down or oscillates side to side. Electromagnetic and mechanical, however, actually describe the properties of that specific wave. Electromagnetic waves are the types of waves that are emitted or radiate from an object. It's the radiation we get from the sun, the radiation that nukes food in a microwave, and it's the radiation that can kill people when it's coming out of an atomic bomb. Mechanical waves, on the other hand, are waves that occur because something enacted a force on a material and a ripple effect occurred. It has to travel in some form of material. It can't just travel in empty space by itself. These are the main properties you need to know about electromagnetic and mechanical waves. Let's start with electromagnetic. So I already said electromagnetic is radiation. We call that radiant energy. It's actually emitted or comes out of an energy source like the sun. These types of waves are only ever transverse waves. They only ever oscillate up and down. More importantly, these types of waves can travel through a vacuum. And when I say vacuum, I mean empty space. Leave Earth's atmosphere where there's no longer air molecules, and you can't hear sound, but you can still have light traveling because light is an electromagnetic wave. The last thing is that electromagnetic waves all have the same speed when they're in that vacuum. It's something called light speed, and we're going to talk about that in a couple slides. Mechanical waves, on the other hand, we're going to talk about a little bit more in a couple of days. The big thing that you need to know right now is mechanical waves must be traveling through some form of material. In other words, a sound wave has to travel through air because it's the air molecules that are actually doing the oscillating. Let's see if you really understand what I was just talking about. So let's say we have a fire that emits light and heat as a wave. Is this an electromagnetic or a mechanical wave? If you thought electromagnetic, you're correct. The key word here is emits. A fire is an energy source, and it is radiating light and heat energy as electromagnetic waves. Now let's say we have two tectonic plates. They slip past one another, creating seismic waves that travel through the ground. Is this electromagnetic or mechanical? If you said mechanical, you were right. The key thing here is they travel through the ground. They're not traveling through empty space. They're not being radiated. It's actually the ground that's oscillating back and forth. Now that we've been able to tell the difference between electromagnetic and mechanical waves, we're going to solve for the wavelength or frequency of an electromagnetic wave. One of the main characteristics about electromagnetic waves is that they all travel at the speed of light when they're traveling in a vacuum. And again, vacuum's just empty space. The speed of light is 3.0 times 10 to the 8th meters per second. No, don't memorize that. I'll always give it to you. But that is an important constant to be aware of. So, when we think back to our old wave equation, now we're, instead of using speed equals frequency times wavelength, we're going to use the speed of light is frequency times wavelength. it means that we can solve for either frequency or wavelength of an electromagnetic wave without being given its speed, because we know they all travel at the speed of light. Here's an example. Red light has a wavelength of 650 nanometers. Determine its frequency. Here's how you solve that problem. We know light is an electromagnetic wave. It travels at the speed of light, c, which is 3.0 times 10 to the 8th meters per second. We're trying to determine its frequency, and I know 650 nanometers, remember I've got nano memorized now, is 650 times 10 to the negative 9 meters. Divide on both sides. I remember to put those things in parentheses in my calculator, and I calculate my frequency to be equal to 4.61 times 10 to the 14th hertz. Are you ready to try one? Here's a problem I want you to try on your own. Read the problem, pause the video now, and then play the video again when you're ready to see the answer. Did you get 3.0 times 10 to the negative 10th meters? If so, you're correct. If not, the work is shown. Pause the video now, see if you can follow where you went wrong. Now that we've mastered how to solve for the frequency or wavelength of an electromagnetic wave, now we're going to talk about the energy of a photon in a vacuum using Planck's equation. And that's a lot of vocab. Let's talk about what it is. So first, a photon, just like we went over back when we talked about forces, it's an elementary particle. It's what carries the electromagnetic force. And in carrying that force, it carries energy with it. As a result, we have to be able to calculate the energy carried in electromagnetic wave. Now, a fancy guy named Max Planck, who's a pretty famous scientist in the physics and chemistry world, discovered that energy of an electromagnetic wave increases as you increase the frequency of that wave. He discovered that the energy of that photon is equal to a constant times that frequency. That constant is h, and we call it Planck's constant because Max Planck is a great guy who discovered it. Again, that's not a constant you need to memorize. It'll always be given to you. Now let's see how it's used in a problem. I want to determine the kinetic energy of a photon of blue light, and I'm told that the wavelength of blue light is 475 nanometers. Now I'm looking at my energy equation and I see E equals hf. I don't see wavelength in there at all. So this is a two-step equation where I first need to be able to solve for frequency. In order to do that, I go back to my light speed wave equation and I plug in the wavelength that I have to be able to solve for frequency. Doing that, I get my frequency is equal to 6.31 times 10 to the 14th hertz. Now that I have my frequency, I can just plug and chug to find my kinetic energy. In doing that, I find that my kinetic energy of a single photon of blue light is 4.18 times 10 to the negative 19th joules. 10 to the negative 19th, that's tiny. But when you think about it, it makes sense because light is not just one photon. It's millions and billions of photons that give us the amount of energy that comes from the sun that we can use in solar cells or that plants are able to use in photosynthesis. Now I'd like you to try an example. Read the problem and then pause the video. Press play again when you're ready to see the answer. Did you get that the wavelength is 6.64 times 10 to the negative 11th meters? If so, you're correct. If not, take a look at the work and see if you can figure out where you went wrong. Remember, this is a two-step equation. You need to solve for the frequency first and then the wavelength. Now that we've mastered the difference between electromagnetic and mechanical waves, solving problems using light speed, and calculating the energy of a photon, we're finally going to talk about the electromagnetic spectrum. The electromagnetic spectrum is a spectrum or a range of all of the different types of electromagnetic radiation we currently know of. This can be as simple as a radio wave. That is what we actually listen to when we turn on the radios in our cars. And it can be as high energy and high frequency as a gamma ray, which is what comes out of an atomic bomb in a nuclear explosion. There are a couple important trends I want you to notice about this electromagnetic spectrum. First, you have very, very long wavelengths when you have very low frequencies. This makes sense because all electromagnetic waves travel at the same speed. So as you increase in frequency, you have to decrease your wavelength. The next thing that you'll notice is that the higher up we go in frequency, it takes a hotter object, like the sun, for example, or a nuclear explosion, to emit those kinds of waves. This makes sense because warmer objects have more kinetic energy, thanks to their temperature. As a result, they can emit higher energy photons. This is why it takes extreme temperatures to cause nuclear fusion in the sun, or to cause a nuclear explosion in an atomic bomb. The other thing that you will need to know is you'll need to know the order of these main types of radiation on the electromagnetic spectrum: radio, microwave, infrared, visible, UV or ultraviolet, X-ray, and gamma rays. The reason you'll need to know this is because you'll be asked to compare. Why is it that X-rays allow us to take pictures of the insides of our bodies? And why is it that we can't use microwaves to do that? Let's think logically about that. X-rays have a much, much smaller wavelength. In fact, their wavelength is about the size of an atom. As a result, those tiny waves with their tiny wavelengths will interact with all of the atoms in our bodies, and it will allow us to take a picture of the inside of our bodies. A microwave, on the other hand, that wave is about the size of a human or an insect. It goes straight through our bodies, or it goes around our bodies, and we can't get any detailed picture from a microwave. Let's see if you really understand this concept. If I increase the wavelength of an electromagnetic wave, what's going to happen to my frequency and kinetic energy? Did you think that both frequency and kinetic energy will decrease? If that's the case, you're right on the money. As we increase our wavelength, our waves get longer, more relaxed, more like radio waves, and so we have a lower frequency and a much lower kinetic energy. Last question. Why is it that gamma rays are more dangerous to humans than microwave rays? This one's tricky, but it's very similar to why X-rays can take pictures of the insides of our bodies and microwave rays can't. Microwave waves have a longer wavelength. They have a lower frequency, less energy, and more importantly, because they have that longer wavelength, they just pass right by our bodies. Gamma rays, they have tiny wavelengths on the order of the size of an atom's nucleus. It can do a lot of damage to our cells because it's about the size of one of our cells. That's why it's so damaging to our DNA and can cause cancer. Let's look back at our objectives. Today, you learned the difference between electromagnetic and mechanical waves. You looked at light speed, you looked at Planck's equation, and we just talked about the electromagnetic spectrum and specific types of electromagnetic waves. Feel free to go back and replay any portion of this video to get clarification on any of the questions you still have, and otherwise, I will see you Thursday.